Here we go. In this video, we're gonna learn about Prim's algorithm. So here we have a graph. So in this graph, we have to connect all the vertices, and we have to find MST. MST is a minimum spanning tree. It means we have to connect all the vertices with taking minimum weight. So this is a weighted graph. So we have to take minimum weight. So you can assume it like you have to visit from point A to point B, but there are multiple routes, but you have to take the smallest route, smallest distance route. So this is the MST. So let's look at the problem. We have minimum spanning tree. So you have given a weighted, undirected and connected graph with V vertices and E edges. Our task is to find the summation of all the weights of the edges in the minimum spanning tree. The graph is represented by urgency list where each element, this is a vector containing vector of integers. So I hope you are already familiar with the urgency list concept. Then each vector represents a edge with the first integer denoting the endpoint of the edge and the second integer denoting weight of the edge. So you have given list, list, then inside we have a array. So you have uh, like this. So for 0, 0 is connected to, in my case, 1, 2 and 4. So here 1, then its weight, then we have 2 its weight, and 4 its weight. So something like this. So connected with 1 with weight 1, connected with 2 with weight 2, connected with 4 with weight 7, and same as this for 1, 2, 3. So this is my adjacency list. So let's look at the problem. Let's look at the example first. So you have given this test case. So the minimum weight that we have to that we have to take to connect all the vertices is 4. So 0 is connected to 2, then 2 is connected to 1. The minimum weight in a minimum spanning tree is 4. So this is the explanation. Then we have this. So there is only one edge. We have to take this edge anyways. So let's build the approach. How to solve this question using Prim's algorithm. So what is a Prim's algorithm? So let me tell you. So minimum spanning tree, first of all, let's talk about minimum spanning tree for a few minutes. So we have this tree, and let's side this tree little bit. So we have multiple spanning trees here. So like 0 is connected to 1, then 1 is connected to 3, it is connected to this, and it is connected to this. So this is a valid spanning tree, but this can be not a minimum. So another is this. So this is a spanning tree. Another way another way to connect all the vertices is this. So this is also a spanning tree, but we have to find the minimum spanning tree. So the weight of the edges should be minimum. Here what we have, this and this. So the total, uh, we have to calculate the minimum spanning tree. So let's find out. You can start from any given node. So I will start from 0 node. So you can start from any given node. So here we have from here we have to visit the neighbor nodes who has minimum weight. We have to visit neighbor node who has minimum weight. So there are multiple nodes connected to 0, but I will take minimum. So how do we identify minimum? So we will take priority queue. So first of all, 0 is connected to 1 with weight 1. Then it is connected to 2 with weight 2. It is connected to 4 with weight 7. So this is my minimum priority queue, and it is comparator is based on 1. So this is my weight. This is neighbor weight. This is neighbor distance. this is, sorry, this is neighbor node, this is neighbor distance. So first of all, what's the distance that we have to anchor to reach node 0? So we are starting on node 0 starting, and ending node is same, so no weight is considered to reach 0. So first of all, what I will do is I will uh, so I will do what I will do is I will start from this particular node. So I will just add 0 and 0. So this is on the 0th value we have neighbor node, and on this value we have neighbor weight. So neighbor node. So I will pop out this value. Only I have a single value. Then I will visit this. I will visit this. Then we have this spanning tree. I am building a spanning tree side by side. So what are the neighbor nodes? I have visited this. So let me circle out. I have visited this. What are the neighbor nodes? First is this, then is this, then is this, and all three of them is unvisited. So we will add all three of them. 2 with 2 and 4 with 7. Then what I will do? So first of all, we have visited array. I hope you are already familiar with the visited boolean array. If you are not, I will talk about it. So boolean array is just for visiting or marking whose whichever node is visited. So then we will pop out. The minimum is this, so we will pop out this value. So 1, it will connect with 1. We are not interested in connections, we are just interested in the weight. So this is just for visualization, and it is not literally connecting. We are just interested in the weight. So we have taken one weight and we have marked this. Then what are the neighbor nodes who is unvisited still now? So this is visited, so we will not consider this. Neighbor is this, but the neighbor is visited. Then neighbor is this, so we will add or consider this. Then another neighbor is this. It is also unvisited, so we will consider this. This is also unvisited, so we will consider this. Then we will pop out minimum weighted value. So this is minimum weighted value 2 and 2. So 2 and 2. This is just for visualization. We don't have to literally build the spanning tree. 2 with 2. Then just mark this. I have marked this. Then what are the neighbor vertices? So this is visited neighbor. This is visited neighbor. This is unvisited neighbor. Neighbor and its weight. This is unvisited neighbor. Neighbor and its weight. Then it's time to pop out a value. So the minimum value is this according to weight. So 2 with 3. So what we have? We have this 2 and 3. 2 and 3. We are again getting 2. Neighbor node. We are again getting 2. But this 2 is already marked. This 2 is already marked. So it is connecting like this. We don't have to connect 2 again. So we will not, although we will pop out this value, but we will not connect. We just have to check 2 and 3. Is this already marked? Yes, it is already marked. We have already considered the the popped node. So we will not consider its corresponding weight. So we will just ignore this. I hope you got my point. Why we ignored this? Because 2 is already considered in MST. Then again pop out a new element. So we have 3 and 5. So 3 and 5. Is 3 already connected? No, 3 is not already connected. So we have to consider the weight. So we will consider the weight. Then just mark this. I have marked this. Then check its neighbor. Its neighbor is visited. Its second neighbor is also visited. So we cannot do anything. Then it's time to pop out a value. So either this element will pop out or this element will pop out. So why we have two similar values? Because first it is connecting with this 2 with 4 with weight 7, then 0 with 4 with weight 7. That's why we have two separate things, elements. So then any of them will pop out. So 4 and 7, so it will connect with 4. 4 is not already marked, so then we will consider the weight. Then we have to mark the 4. What are the neighbors of 4? 1 already marked, 2 already marked, 0 already marked. Then we will not add anything, then this element will pop out. But in this case 4 is already marked, so we don't have to join 4 again. We don't have to do that because 4 is already joined with some other vertex. Then we have 3 8. So 3 8, 3 8, 3 is already joined, 3 is already considered in MST. Then we have 4 9. 4 4 is already considered in the MST. So we have considered each and every vertex, and we just while we were popping out the elements, we just need to consider the corresponding weight. So we have considered this weight, this weight, this weight, this weight, and we have added the weights in a variable called answer. So what are the total is 15. So 15 is our MST. MST is just a value. So we have considered the MST. Then one thing to notice here is one thing optimization you can do. So we have marked all 5 nodes while popping out a value. If the popped neighbor popped node is not already visited, so then we are considering the answer. Then what you can do, you can also increment your count pointer. Count will check how many nodes have you visited till now, and if you have visited all the nodes, so you don't have to pop more values because you already know you have joined v vertices. So you don't have to pop out more values, more elements, so you can directly return the answer. So this is just a slight optimization. So now let's code this. We have prims. So we have prims. In this we have this essential list. Then we have a priority queue. Priority queue is based on one. So I am adding two things. First is the node, second element is the weight. So we are accessing with the minimum weight. So this is the comparator. Then initially we are adding 0 and 0 because to reach 0 node, 0 is our starting point. To reach the starting point itself, we don't have to take the distance. So that's why. Then we have visited array for marking. Then we have answer. Priority queue is not empty. Then we are just popped the value. Current node is present on 0th index and weight is present on 1th index. If it is already marked, the popped value is already marked, then just continue. Else consider the weight and mark the node. After that just traverse in the neighbor nodes. So this is the neighbor node. Neighbor node is present on 0th and neighbor weight is present on 1th. If neighbor node is already visited, we don't have to do anything. If it is not already visited, we need to consider that edge. We need to consider that edge. So neighbor node with the corresponding neighbor weight. Then just return the answer. So let's talk about the optimization thing. We have a counter, and every time we have visited a unvisited node, just increment the counter, and if counter reaches n, we have visited all the vertices, then just return the answer. We don't have to do this for loop, we don't have to run the for loop, and we don't have to pop each and every element in our priority queue. So now let's submit this, and side by side let's talk about time and space complexity. So first we have a priority queue. So priority queue contains edges. Priority queue contains edges. So it contains um, edge, node, and its corresponding weight. So it will contain log e. Log e means edges. So for adding and removing value from our particle, it will take log e, and we have this for loop also. So this for loop will visit each and every edge itself. So the total time complexity is e log e, and space complexity. We are adding the edges. So space complexity is also log, order of v. Space complexity is not v square. Why it is v square? It is not v square. We have only v. The space complexity is only v, or v. So let's talk about space complexity. We have order of v, or we also have a boolean array, which is uh, boolean array is for v, and for priority queue we have e. For a priority queue we are the maximum element we have is edges. So this is for priority queue, this is for visited array. So it will be maximum of v or e. So this is the time and space complexity. Code is given in the description.